Let's summarize the mathematical model before we look at how to solve it numerically using the finite element method. Our mathematical model consists of governing equation and boundary conditions. We'll take a look at the governing equation first, and then we'll take a look at the boundary conditions. The governing equation is that, as we saw in my derivation of the equation, and from the derivation we know that that term represents the net heat flow through the faces of an infinite simul control volume. That is a vanishingly small control volume. And that term represents a heat generation within the control volume. And this is, both these terms are written per unit volume, and they have to add up to 0 for energy conservation. And they're defined, and this equation is defined from x equal to 0 to x equal to L. That's because our bar is of length L. And we need to put boundary conditions at the edges of the domain. So this is called the domain. When we go into answers, we'll be specifying the domain by drawing the geometry, but this is what we're specifying when we draw the geometry for a lot of problems. The boundary conditions, first let's take a look at the left boundary condition. So we say that at the left boundary we know the temperature at some value T sub 0. So that's a value at that face. And at the right face we have the heat flow per unit area. That's a heat flow per unit area. So that's the boundary condition at the right face, and we know that value. And I should make it clear that this is heat flow per unit area. It's called heat flux. Earlier I used Q for heat flow, and now I'm using it for heat flux. My bad notation. So you have to be careful, whether what we're talking about is heat flow or it's a heat flow per unit area. In this case, it's a heat flow per unit area. And that's related to the temperature gradient at the right boundary through the Fourier's law. So essentially what we have here is the temperature gradient at this boundary. So we have the temperature here and we have the temperature gradient here. And the two major kinds of boundary conditions you have are the value or the gradient of the value. So this mimics both the major types of boundary conditions. Governing equation plus boundary conditions is called a boundary value problem. So let me write that down because it's a very important idea. So this is called a boundary value problem. It's governing equation or governing equations defined in a domain and boundary conditions defined at the edges of the domain. So to complete the boundary value specification, we need the governing equation, we need the domain, which we in the tool we'll be specifying in the geometry step, and then we need boundary conditions at the edges of the domain. The exact solution to this problem is straightforward. It's a simple linear differential equation, and I presume you've seen it while studying calculus. So let's think about how to solve this using the finite element method in order to understand the finite element method. That's what I'm going to talk about next. We'll do 3 case studies using the ANSYS finite element analysis solver, which uses the finite element method. And before we get into the ANSYS finite element solver, we need to understand the major elements of what's under the black box so that we can move beyond just pushing buttons and use the tool effectively. In particular, we need to understand the strategy used by the finite element tool to solve whatever mathematical model we give it, and what are the errors introduced in the process, and how do we decrease these errors. And I'm going to present these ideas from the perspective of the tool user rather than the code developer. Whereas, conventional finite element analysis or finite element method introductions tend to present the material from the viewpoint of the code developer. And to figure out what concepts to cover, I've used a just-in-time strategy, which is I've gone through the ANSYS case studies and distilled out what one needs to know as one is working through the tool, what one needs to know about what's under the black box. And I'm going to present these ideas intuitively and visually, so I'm not going to do the derivations, rigorously, but intuitively, so that by thinking in an intuitive and visual way, I found that when I'm in the tool, it's effective to figure out what the tool is doing, how do I reduce errors, how do I fix problems, and so on. Whereas on the other hand, I've seen that, when one sees the gory detail, I've seen this, often with students, it's, you see all the gory details of the finite element derivations and so on, and you get to the tool, it's a very different context, and, it's hard for us to kind of transfer it from that, from the textbook context to the tool context. And so what I'm trying to do here is bridge the two. We will discuss the big ideas in finite element analysis by considering a simple example, one-dimensional heat conduction in a bar. More complex examples that we'll be doing in the ANSYS tool are based on these ideas. And we'll come back to these ideas as we are solving problems in ANSYS. They form the building blocks of the finite element method. So it's important that you understand these ideas well to use the tool effectively. Let me go to my PowerPoint slide. Here's the simple problem that we'll consider. We have a bar of some given length, and we have heat conduction in the bar. We are interested in finding the temperature distribution in the bar due to heat conduction. We'll assume that the problem is steady, that is, the temperature at any point doesn't vary with time. We will also assume that the problem is one-dimensional, and which means that the temperature for any cross-section is the same, and there's no variation of the temperature across the cross-section. So if I put a coordinate system like that, with that being the x direction, that being the y direction, and that being the z direction, I will have variation only in the x direction, and the temperature won't depend on y or z. And once I find the temperature at any point in the cross-section, I know the temperature anywhere in the cross-section. That's what I mean by the one-dimensional problem. And these simplify the equations that we need to solve, and so the details are kept to the minimum as we focus on the big ideas. If I go back to the pre-analysis framework that we saw before while discussing what's under the black box, the first thing we need to think about is what is the mathematical model to be solved. And then we'll talk about how to solve that mathematical model using the finite element method. And the mathematical model consists of governing equation, which is a differential equation, and boundary conditions. Let me talk about the governing equation. Going back to my graphic of the example problem, this indicates a tiny volume within the element, a vanishingly small volume within the element, okay? It's called a control volume, and in my next slide, I consider this volume. And let's say, the dimensions are delta x, delta y, delta z, this being the x direction, this would be y, and this would be z. And I'll look in the limit as these are almost zero, okay? These tend to zero. And that's why you say it's an infinitesimal control volume. Now they're almost zero, but they're not zero, because the whole framework falls apart if they become zero. That's a trick in calculus. It's almost zero, but not zero. And it took me, several years to figure out that that's a trick it's playing. And then let's do an energy conservation for this infinitesimal control volume. Let me consider this phase here. And there is a heat flow through that phase, which I will denote as Q sub x. And then there's a heat flow, actually this is a heat flow in, and then there is a heat flow out through that phase, which I will denote as Qx plus, so it's going to be, it's going to be slightly different from that, because, that distance is vanishingly small. And that change I can find from the gradient. So if the rate of change of Q sub x is that, if I multiply it by the distance, I'll get how much it's changed. Okay, and so that's a small difference. And you're going to get higher order terms, that are going to be proportional to delta x squared, delta x cubed, and so on. But in the limit, as delta x tends to 0, I can ignore that. So that's why this is, this is important, because I can ignore the higher order terms. Okay, so the heat flowing out is slightly different from the heat coming in. And I can write the net heat flow out is going to be, okay, this is going to cancel that, so it's going to be just the change from this phase to that phase. That's given by this term here. Okay, so that's that term. And now I can relate that to the temperature using Fourier's law. And many of you should have seen this before. It's like the foundation of heat conduction, which says that, the heat flow is proportional to the temperature gradient. Okay, so if the temperature gradient was larger here, you'd get more heat flow. If there was no change in temperature near that phase, then there would be no heat flow through that phase. I think that's intuitive. And there's a constant of proportionality, which is k, and I get a negative sign. And the negative sign you need because temperature, the heat flows from higher temperature, lower temperature. That is in the direction of the decreasing temperature. That's what that negative sign indicates. K is called thermal conductivity, and we'll assume that it's a constant. Okay, and this term gives me per unit area. So I need to multiply it by the area of the phase, which is going to be delta y delta z. Okay, so that's that area, and I'll get the net heat flow through any phase. So now if I substitute that back in here, okay, I'll get the net heat flow out in terms of the temperature. But one thing to note is, when I substitute it back, I have to differentiate this. So what will happen is I'm going to get a second derivative of the temperature. So let me do that. I'll get a term. So the purpose is not to derive this rigorously, but to do it intuitively so that you get a sense of what the physical significance of each term in the equation means. So you're going to get a term that looks like minus k d squared t dx squared, and then you have, delta x from here and delta y and delta z from there. Okay, that's, so this represents a net heat flow through the phases. And I'm going to be assuming 1D. So let me list assumptions here as I'm going along. So I have assumed one-dimensional. So I'm going, I don't need to, I'm saying that there is no heat flow through these phases or through this, this phase. one-dimensional or 1D. I also have assumed that there is no variation of the temperature with time. So I'm assuming that it's steady. And I'll also assume that K is a constant. That is, we have constant thermal conductivity. We can relax all these assumptions, but just make the details more complicated. And I also say that there is another term contributing to the heat, which is the heat generation. So I have some heat generation per unit volume, which I call Q. And so the net heat out, and Q, this is per unit volume. So the net heat out is going to be what's flowing out minus what I'm adding through heat generation. So that's going to be minus Q, and that's going to be proportional to the volume. Okay, that's per unit volume. So that's going to be delta X, delta Y, delta Z. Now one key thing to keep in mind is this term accounts for what's coming in through the phases. This term, which I'll add here in a moment, accounts for what's coming into the volume. Okay, so they're different that way. One is related to the surface area, the other is related to the volume. And if I bring that in here, I'll get minus Q, delta X, delta Y, delta Z. And if energy is conserved, and I have no other effects, the heat going out plus minus the heat added should be equal to 0. And I can divide through by delta X, delta Y, delta Z, and I'll get my final governing equation, which will look like K d squared T dx squared plus Q is equal to 0. Okay, that's called the heat equation, and that represents energy conservation for an infinite small control volume. That's a governing equation. We need to, and this is going to be defined over the length of the bar, and we need to add in the boundary conditions, which I'll do when I summarize the mathematical model. Now that we know what's the mathematical model that we want to solve, governing equation and boundary conditions, i.e. a boundary value problem, let's take a look at how to solve it numerically using the finite element method. So I'm moving from talking about the mathematical model to talking about the numerical solution procedure, and how through the numerical solution with the finite element method one can calculate selected variables at selected points. The first thing we do is discretization. Let me unpack that idea. We reduce the problem to determining temperature values at selected locations. That's the bar I have, and I need to determine the temperature along that line. I've reduced it to a one-dimensional problem, so I need to determine temperature only along a line. So I need to determine the function t of x. And I say, you know what? Instead of determining temperature everywhere along that line, I'm going to determine only at selected locations. In particular, I'll determine it at 4 locations. 1, 2, 3, 4. And everywhere else, I will just use an interpolation. So if I want to know the temperature here, I'll use an interpolation between that value and that value. If I want to know the temperature, let's say here, I'll use an interpolation between that value and that value. It's a linear interpolation. So which means that if I plot the temperature versus x, okay, and these, are my 4 values, then in between, it's just a linear interpolation. I don't know these values yet, but I know the shape. The shape is going to be that. So I've reduced the problem to determining temperature at 4 points. So instead of determining an unknown function, I'm going to determine 4 values. That's called discretization. And it's easier to determine, a finite number of values rather than a function. Determining unknown functions is hard. Determining a finite number of values is not as hard. And in terms of terminology, these are called nodes. Okay, that's what I have here. And these are called elements. So I've divided my domain into 3 elements. And I have 4 nodes. And in the process, what we have done is we have assumed a shape for our function, and that shape consists of piecewise polynomials, piecewise linear polynomials. And these, the shape is constructed element by element. And in any finite element, methodology, you do that. You're assuming a shape, and the shape is constructed element by element. The crux of the problem now is how to determine the temperature at the nodes, in our case at the 4 nodes. Let's talk about next. Let's look at how to derive the system of algebraic equations starting from our boundary value problem. So we have our differential equation and we have boundary conditions, which I haven't shown here in the interest of brevity. And we have the shape for the temperature that we have assumed. So the first thing that occurs to me is that, okay, you know what? I can take that shape, that is my piecewise polynomial approximation for temperature, and I can plug it in here, and maybe I'll get my system of algebraic equations in the nodal temperatures. And I tried that, and it turns out it doesn't work. As the kids in my daughter's school would say, eh. Okay. By the way, textbooks don't tell you that, okay? They don't tell you that this approach doesn't work. And in fact, it's quite easy to see that it won't work. So here I have a linear variation. And if I differentiated that twice, I get 0, which means that that's 0. According to this shape, that's 0, but my heat generation is not 0. So it's saying Q equal to 0. That's wrong. It's even worse at the nodes because your slope is discontinuous, which means that the second derivative is not, the first derivative of temperature is discontinuous, second derivative is not defined. So this approach doesn't work. In fact, you can see that there is no way with this shape I can satisfy my differential equation. In fact, it will satisfy it very poorly with this shape. So what do I do? Here's what people have figured out. Okay, so you know that this approach doesn't work. So what you do is you go from the differential form to a weighted integral form. So this over here is our differential equation. So you take the differential equation, you multiply it by a weighting function, okay? And that weighting function is an arbitrary function. So this is an arbitrary function. And you integrate it from over your domain. So in our case, from 0 to L, and that should be 0. The exact solution is going to satisfy that for any arbitrary W, and it's also going to satisfy that. But once I've assumed a shape for the temperature, there's no way I can satisfy this for any arbitrary function. So what do? I say, you know what? I won't satisfy this for any arbitrary W. I'll satisfy it for one particular shape of W. So I'll say, hey, instead of satisfying it for arbitrary function, I'll satisfy it for an arbitrary piecewise polynomial function. That means I assume a shape for W that looks like like the shape for temperature, and we'll see that in a minute graphically. And then when I have this form of, when I've approximated the weighting function that way, so I have a shape for temperature, I have shape for W. Now if I plug in that shape into this, out pop my system of algebraic equations in nodal temperatures. And we'll see this, we'll unpack this a little bit more. But there's an important takeaway here. That is, my finite element solution will not satisfy my differential equation exactly. In fact, in this case, it satisfies it poorly. It won't satisfy this weighted integral form for any arbitrary W, but it'll satisfy the weighted integral form for a particular form of W. And and one can show that as I use more nodes, this becomes more and more arbitrary. So it's going to it'll tend to the exact solution, and we'll come back to that. Okay, so which means that to summarize then, we have the weighted integral form, the weak form as it's called, but with a particular shape of W. So our temperature over here is this shape. Our weighted integral, our weight is of this shape, and you can see it's it's the same kind of shape. So we assign values for the weights at the nodes, and then we just do a linear interpolation. And if we plug these two shapes in here, out will pop our algebraic equations, and we'll get the number of algebraic equations that we need to determine the nodal temperatures, and we'll take a look at that. So we'll look into some of the details of this process, and it'll give us some very important insights that we can carry into the case studies, the finite element case studies that we'll do in the answer solver. How to find the nodal temperatures. In our case, we have 4 nodal temperatures to find, and we have our mathematical model, that is the boundary value problem. And so we'll go from the boundary value problem, that's differential equations plus boundary condition, to a system of algebraic equations in the nodal temperatures. So you're going from differential equations or differential equation to a system of algebraic equations. And you derive that system of algebraic equations using the piecewise polynomial approximation for temperature that we saw previously. And each equation will relate a nodal temperature to its neighbors. It's going to be a linear equation, and so for instance, if I write the equation at this node, it'll relate the temperature T2 to T1 and T3. It won't involve this temperature, for instance, and this becomes significant as you get more nodes, and so the equations will relate only the immediate neighbors. So we are going from calculus to linear algebra. And the system of algebraic equations can be written in matrix form, and usually you see this form written. T is a vector containing a nodal temperature. So in our case, T is going to be T1, T2, T3, T4. So that's what that's going to look like in our case. This is called the stiffness matrix. It comes from structural mechanics, which we will see later, and that's the force vector, and the boundary conditions will affect that. The heat generation term will affect that. Again, bad notation. That's not the heat generation term that we saw earlier. And then, so if we have a system of linear equations, we can solve that. That is a matrix inversion problem. So we'll invert that system of linear algebraic equations, and we'll get our nodal temperatures. Okay? That is our selected variables at selected points. And once we know the nodal temperatures, we can derive everything else from those 4 nodal temperatures through post-processing. So if I want to know temperature at any arbitrary point, right, if I want to know the temperature here, I can just use my interpolation to find that. So this I'll do by interpolation, and then I can differentiate my interpolation to get the heat flux, that is the heat flow per unit area. And then the crux of the problem reduces to how do we derive our system of algebraic equations such that it best satisfies our mathematical model. We can't satisfy a boundary value problem exactly, but we want to satisfy it the best we can. So we'll take a look at that next. Next, let's take a look at the heat generation term in the weak form. That's this term over here. This is in general called a source term. So you'll see that terminology being used. And source terms have, it's basically a known function. And here, it's a constant, but it could also be a function. In structural mechanics, this could be gravity. So that would be a source term. Or in the wind turbine blade example that we will do, the centripetal acceleration is going to be applied in this way. It will be a source term. And if we integrate this term, we have to do the integration again element by element. And let's do it over the first element. I can take q out of the integral. So I'll take q out of the integral and I'll say 0 to delta x. So delta x is that distance times, so the weighting function times dx. So it just becomes an integral of the weighting function, and that means that I need this integral will give me this area. And you can work out what that area is, and that comes out to be q. You'll get w1 plus w2 times delta x divided by 2. That's the area. And I can, split this into the part that depends on w1 and w2. So the part that depends on w1 is going to be q delta x over 2, and the part that depends on w2 is going to also be q delta x over 2. If I multiply this by a, which is equivalent to multiplying this by a, in fact, that's what when you do the procedure rigorously, that's what you would do it. This term, so the term q a delta x, so q is the heat generation per unit volume, and that's a volume, that's heat generated in the element. And in this case, that would be for any element because the element lengths are all the same. So this is interesting, right? That when you integrate that term, what happens is you can interpret that as the half of the heat generated is assigned to this and half of it is assigned to this. So if I divide this into 2, half of this heat generated gets assigned here and half of it gets assigned here. And similarly for element 2, half of this will get assigned here and half of this will get assigned here. And so when you work it all out, what happens is that for W1 you'll get only one contribution, so it'll just be Q delta X over 2, plus for W2 you'll get two contributions, this one from the first element, and then you'll also get a contribution from the second element. So that'll be Q delta X over 2 plus W3 and so on. You can work it out. And let me go back to the, I showed all the equations that were multiplied by the weights. So you can see how this term comes about. Okay, that's half of the contribution here. You can see how this term comes about. That includes both of these contributions and so on. And if you write this in the in this form, that's the stiffness matrix form. This is how it's usually written. By the way, I noticed that I've called early in one of my earlier slides, I called this Q, and now I'm calling it F. Sorry about mixing notations on you. It's the same thing. But what this means is that the heat generation or the source term is going to affect all the rows of F because it appears in all the equations. This is in contrast to this term that's going to affect only the equations at the boundaries. So that gives you some insights into how the source term gets incorporated into the algebraic equations. Let's now take a look at the second term in the weak form. That's this term over here, and it involves the derivative of the weighting function as well as the temperature. So my temperature variation is that, and the corresponding variation of the derivative of the temperature is that. And since we have a linear interpolation, the derivative is constant over each element. For instance, if I want to know what is this value, the derivative over here, it's just going to be, this value minus this value divided by the length of the element. So that value is going to be T2 minus T1 divided by delta x, correspondingly for this element and so on. And that's the derivative of the weighting function, and again that's going to be piecewise constant. For instance, this value here is going to be W2 minus W1 divided by that distance, which is delta x. And then I'll have to go and figure out what it is for the second element and so on. And then I need to plug these variations in here. And let's say I'm doing it over the first element. This is constant, and k is constant. So I can bring all of this out of the derivative of the integral, and I'll just get integral of dx over the element, which is the length of the element. And this, so I have to multiply this by this, and W1 is going to multiply T2. It's also going to multiply T1, so I'm going to get, terms such as W2 or W1 T1 and W1 T2, similarly for W2 as I've talked about before. And when you look at the the stiffness matrix form of it, what this means is these terms will go into appropriate rows and columns of the stiffness matrix. So you have to do the bookkeeping, like, okay, this term, I know that it's going to go into the first row of the, whatever coefficient I have here will go into the first row of the stiffness matrix. Which means that this term affects the stiffness matrix, whereas these two terms affect the force vector on the right-hand side. And there's a very important takeaway from this, which is if I want to know the algebraic equation at this particular node, which temperature values will involve? I'll say, okay, it's going to involve, so I look at what all W2 is multiplying. W2 is multiplying T1, it's multiplying T2, that comes from integral over the first element, and then W2 will multiply T2 in this integral, but it'll also multiply T3. Which means that when I write the algebraic equation, when I collect terms, the algebraic equation at this node will involve the temperature value here, and it'll involve the temperature value here and the temperature value here. It won't involve the temperature value here. And we can come up with a general principle. So we look at, okay, the algebraic equation here will involve this node, and then we will temperature at this node, and then we will look at the elements that are connected to that node. So I have this element connected to the node and this element, and then I look at what are the nodes connected to that element. So I have this node here that's connected to that element, and this node here that's connected to that element. And I can deduce that the algebraic equation at this node will involve these three temperatures. And I can generalize this. So I have this complicated mesh in ANSYS, and I'm thinking about, okay, this node is connected to these elements, and then those elements in turn are connected to these nodes, and so I know this node, ANSYS will write relationships connecting the temperature at that node or displacement when we go to structural mechanics to all the corresponding nodes. And I feel like that's very useful when I'm in ANSYS. Here, what I'm going to do is I'm going to show you the process by which you go from the weak form to a set of algebraic equations. And it's really the heart of the finite element method. And I didn't understand this for the longest time. I'm trained in CFD and in fluid dynamics and in the finite difference method, which is actually not used very much in industrial codes. And so what I did was, to understand this process of going from the weak form to the algebraic equations in the finite element method, I just shut the textbook. And I said, I'm just going to work it out myself. And in the process, I begin to understand, oh, these are the tricks that are happening. And then now when I'm in ANSYS, I'm using these insights all the time. So I'm going to share those insights with you. And I'm trying to do this very, graphically, because usually it's presented this as with a lot of algebraic a lot of equations and so on, which really I think takes away from the understanding. Okay, so we have our weak form, which is over here. And we have our domain divided into 3 elements. So you can think of each element as a segment of the domain. And we have the assumed shapes for the temperature and for the weighting function. And we want to satisfy this equation for these shapes. And when I do this integration, and I'll do this integration element by element. So when I do the integration over the first element, I'll get terms where I'll have W1 multiplying T1, and I'll also get a term where W1 multiplies T2. Okay, so I'll get a term that involves W1 times T2 and W1 times T1. And you'll have some, constant coefficients here, which you have to work out. It's going to depend on K, and it's going to depend on this element length. We won't worry about what that, what that constant coefficient is. And interestingly, when you go and do the integration over the second element, you won't get any terms involving W1. Okay, so those are the only 2 terms where you get W1 multiplying a nodal temperature. Then when I go to, let's consider W2. So you'll get a term, when you do the integration over the first element, you will get a term where W2 multiplies T1. So you'll get a term like that. You will also get a term where W2 multiplies T2. And then when you do the integration over the second element, you will get W2 multiplying T2, so that you can clump in over here. And then you'll get W2 multiplying T3. Okay? But you won't get any terms where W2 is multiplying T4. So you see these terms, W's will multiply only the neighboring nodal temperatures. And then it's like you get all these terms and you put them all together and you organize them in a particular way. And I've done that here. And I'll unpack this. Okay, so this is a lot of terms. So let's look at the first row here. What I've done is I've shown you if you take all the terms that are multiplying W1 and you organize them like this is what you'll get. Okay, W1 will multiply T1, you'll get some constant coefficient here, it'll multiply T2, it'll multiply, so you'll get a term involving W1 from here. So that's that term here. And then this term is from here. So this term comes from there. And similarly for W2, so at W2 you will get, terms where it's multiplying T1, T2, T3 as we talked about, and then you will get a term from, from there. So from the heat generation term, which is called a source term, but you won't get anything from this one. Okay, so this term affects only, this gradient term at the boundaries will affect only the nodes at the boundaries. So since 2 is not at the boundaries, you don't get that term here. And similarly for W3 and W4, that's equal to 0. Now we are trying to satisfy this for arbitrary W, which means that our nodal values here, these are arbitrary. So if you want to satisfy, this to be equal to 0, for any values of W1, W2, W3, W4, the only way you can do this is each individual term is equal to 0. So which means since W1 is arbitrary, I will set that as equal to 0. And that gives my equation at the first node. So whatever multiplies W1, these terms will contribute to the equation at the first node. Whatever multiplies W2 will contribute to the equation at the second node, and so on. And so that's the process by which you go from the weak form to the algebraic form. And it's also, useful to, as a code user, it's also useful to know how each of these terms, where it goes in the algebraic equations. And we'll use those insights when we are in ANSYS. So that's what we'll look at next. I've given you an overview of how you go from the weak form to a set of algebraic equations. Let's unpack that a little bit more by going to each term in the weak form and see how they affect the algebraic equations. Let's consider the first term in the weak form here. So I've grayed out the other terms, and we are focusing on this term. I need to evaluate this at x equal to L, which is the right boundary, and W at the right boundary is just W4. That's a constant. And dt dx at x equal to L is just the value at node 4. And then I need to evaluate it at the left boundary over here, and I'll get a corresponding term. Let's take a look at this term here. This is related to the flux boundary condition at the right boundary. If you recall, we say that the flux at the right boundary is given and equal to some value. And that's related to here. In fact, that's just going to be minus q times ql from the Fourier's law. Which means that when I, assemble all this into my final equations, and I've shown just, the term that multiplies W4, I will get a term where I have the gradient at the right boundary over here. In fact, I need the k. I missed out the k here. There are lots of details, lots of bookkeeping that you can trip up on, and so I'm glad, ANSYS takes care of the bookkeeping and we can focus on the big ideas. But that's not an excuse for missing out k here. And that's just minus ql. This means that because the gradient at the boundaries appears naturally in the weak form, when you have gradient boundary conditions like heat flux, or when we go into structural mechanics, a gradient boundary condition is the traction or the force, they get naturally incorporated into the algebraic equations. And for that reason, this kind of a boundary condition is called a natural boundary condition. And natural boundary condition involve the gradients of whatever variable one is calculating. And when one assembles these into a stiffness matrix, this is a compact way of writing the equations which I introduced earlier. You can see that the flux boundary condition will get incorporated into the right hand side. In fact, it'll go into the right hand side over here for the equation that you write at this particular node. It won't affect the stiffness matrix, okay? And then this term gives you the flux. So this is the flux that gives you minus flux at the left boundary, which is over here. So it's giving you the flux at this boundary, and that's not known. What's done is you use that term to evaluate the flux at the left boundary, and then you can use that to check energy balance. And in ANSYS, when we compute a reaction, that comes from a term like that, and we will look at that a little bit later, because it's a very important way of checking your results, whether it's conservation of energy in this case, or when we go into structural mechanics, equilibrium. At this point, we have our weighted integral, and we have the assumed shapes for the temperature and the weighting function. And our weighting function is arbitrary, but we have reduced the arbitrariness of the weighting function to the arbitrariness of the values at the nodes. So we want to satisfy this for an arbitrary weighting function of this shape. How do we do that? What we do is we do an integration by parts. So if you have forgotten your integration by parts, you might want to quickly look it up on the internet, and then this might make more sense. So here I've written out what you'll get from the integration by parts, and let me unpack that. So this is the term. So the weighting function multiplied by this is the term that you would do the integration by parts on. So first you will get, you will integrate that, so you'll get dt dx, and then you'll evaluate, this product of this and the integral of that at the boundaries. So there's no integral happening in the first term, it's just an evaluation of the boundaries. And then you get a second term where you take your first function and you differentiate that, that's just the constant, and you integrate your second function, and when you integrate d squared t dx squared, you will get dt dx and dx. So now key things happened, okay? Here I have, in the original differential equation, I have a second derivative for the temperature, but here I have the first derivative. And I know that the second derivative doesn't behave very well, right? So second derivative is 0 everywhere, and it's not defined at the nodes. Whereas the first derivative is defined. It's discontinuous at the nodes. That's not a big problem when you're doing integration. So which means that now I can use this shape in here, but I can't use this shape in my original differential equation. Which means that this has, this form has fewer restrictions on the shape you assume. For that matter, for that reason, this is called the weak form. And the original differential equation is called the strong form. And the key thing is, because you've reduced the order of the derivative by 1. And then you get, that term is just from here. And you don't do any integration by parts over there. And that's equal to 0. And next what we need to do is take these shapes and plug it into this and get our algebraic equations. So that's what we will look at next. We discussed the weak form term by term and kind of tracked the corresponding terms in the algebraic equations that you would get. Let's put it all together. If you do that, you'll get the equation shown here. And this is this equation I showed before when talking about going from the weak form to the algebraic equations. And now we have a better idea of, the genealogy of each of these terms. So we know that when we do the integration over there, we can find out what these coefficients are. We know that from the integrating the source term, we will get these terms here, okay, and that'll come into the that'll multiply all the weights at the nodes. And for this term here, when I evaluate it at the right boundary, I will get this term here, and then when I evaluate it at the left boundary, I'll get this term here. As I've talked about before, these weights are arbitrary, so we want this to be satisfied for any arbitrary choice of the weights, and the only way we can do that is to set each of these to be 0 individually. So we have to set this to be equal to 0. That'll give us the equation at node 1. Similarly, that to be 0, and that'll give us the equation at node 2, and so on. And you'll get the set of equations shown here. So that's the equation at node 1, this is the equation at node 2, this is the equation at node 3, and that's the equation at node 4. And if I look at the stiffness matrix form based on these coefficients here, I will enter them in the corresponding rows and columns of the stiffness matrix. For instance, this would go into the first row, first column, this coefficient of the stiffness matrix. And these terms here would go into the right-hand side, the force vector. So for instance, this whole term here would be the first row of the F vector. One thing we haven't talked about is the temperature boundary condition that we have at the left boundary, how to incorporate that. So we'll discuss that before talking about how then the solution proceeds. Let's look at that. Let's take a look at how the temperature boundary condition gets incorporated into the framework that we have been discussing. And the temperature boundary condition is called an essential boundary condition, and I'll indicate why. This is in contrast to the flux, which is, as we saw, a quote-unquote natural boundary condition. So we have our 4 nodes arranged along a line, and I've shown it within the context of the bar. And this is the assumed shape for our temperature. And we have 4 algebraic equations here relating temperatures at neighboring nodes. And I've brought the equation at the first node onto the right-hand side. The reason I did that is because it involves this term, the gradient, at the left boundary, and that's the heat flux at the left boundary. And that's not known. So this equation involves an unknown on the right-hand side. So I've set it aside. On the other hand, at the left boundary, we know the temperature from the temperature boundary condition. Okay, so now I bring in the additional equation from at node 1 from that temperature boundary condition. The shape that we have assumed has to essentially satisfy that that equation. That is, this value of the nodal temperature has to be T0. It's essential for it, which is why this is known as an essential boundary condition. Okay, that's the terminology, and contrast it to the flux boundary condition here, which you can't say that the shape has to essentially satisfy that. In fact, we'll see that the shape won't satisfy that the natural or the flux boundary condition. So the solution proceeds in 3 stages. So in the first stage, what you do, so this is the first stage. You look at all the nodes that have essential boundary conditions on them, and you just assign the corresponding temperature value. So for here, the solver would look at this node and say, hey, there's an essential boundary condition on that node, and that value of temperature has to be T0, and so you know that value. Now you come to these 3 equations. This is known, but this is unknown, this is unknown, this is unknown. So you have now these 3 nodal temperatures that are unknown, but you have 3 equations. So you have 3 equations and 3 unknowns, and so you solve them together by inverting that subset of the stiffness matrix, and that's step 2. In this case, that would involve inverting a 3x3 matrix. Now people are doing ridiculously large problems, 100 million unknowns. So you're inverting 100 million by 100 million stiffness matrix for very complicated problems. And if you do it cleverly and you have very fast computers, you can do that with today's computers. And then after stage 2, I know all my nodal temperatures. Okay, so all the nodal temperatures have been determined, and I basically know my temperature distribution. Then what do I do with this equation here? It turns out you can do something very important. So in the 3rd stage, you can come to this equation and say, hey, now I know T1 and I know T2, and this is a known quantity, so I can determine the flux at the left boundary. And if I take Q1 and multiply it by the area, that's the amount of heat flow leaving or entering through the left boundary. And I can do I can do a check on the solution, whether the solution satisfies the heat balance or energy balance. So I can check that the heat flow coming in, that's this over here, plus the heat generated, which I know, that's Q times the volume, is equal to the heat going out, which I know from the boundary condition. So this entity turns out is very important to check the energy balance, and it's called a reaction in ANSYS. And you can ask, you can request what the reaction is from ANSYS and then do a check on the energy balance, and you'll be doing that. It's called a reaction because it comes, that terminology comes from structural mechanics, where this entity would be the force at the essential boundary. So if you're if you're fixing the displacement, or you're fixing the left boundary, then this reaction would give you the force that's required to hold that boundary there, or that's a reaction. And this 3-step process is very general, and for any finite element solver is going to use this 3-step process. Step 1 and step 2 are necessary, and step 3 is highly recommended to check on whether your solution satisfies fundamental physical principles such as energy conservation or equilibrium. Earlier, when discussing essential boundary conditions, we saw that we can calculate the heat flux going through the left boundary, and that's a boundary at which we have our temperature or essential boundary condition. And at this point, I know the temperature at node 1. That's anyway known from the boundary condition. I know temperature at node 2, so I can back out what that heat flux is, and that times, the heat flux times the area would be what ANSYS would report as a reaction. And if I plug in the numbers, I get that the flux at that boundary is minus 5.5 watts per meter squared. And I picked K to be 1 in SI units, so dt dx is just the negative of that, and that's 5.5. And it turns out it matches exactly with what you get from the exact solution. The implication is that the reaction that I calculate matches, so it's getting Q out exactly right. And that's times area is the amount of heat going out through there. The amount of heat going in is Q in times A, and that's specified. And then we also have the heat being generated times the volume. Okay, I'm indicating that as the volume. So this is specified, this is specified, this matches the exact solution. The implication is that energy is conserved for the bar. So the energy is conserved in aggregate, and this is when I'm looking at the energy coming out calculated using the discrete equation. That's the equation from the weak form. So energy is conserved in aggregate, but that doesn't mean that it's conserved for each finite element or it's conserved for each infinitesimal element. And when we go into answers, we'll do a 2D conduction problem, and we'll see how these ideas can be extended to 2D, to the 2D case. For our simple model problem, there is an exact solution, and we can compare the finite element solution to the exact solution to see how the finite element solution is doing. Here is a comparison of the temperature between the finite element and the exact solutions. On the vertical axis, I've plotted the temperature. On the horizontal axis, I've plotted the distance along the bar. The black line is the finite element solution, and the symbols indicate the nodal values. And the dashed red line is the exact solution. And we see that the nodal temperature values are exact. So if I look at this nodal temperature value, this nodal temperature value, and this nodal temperature value, they match exactly with the exact solution. That turns out to be an unusual property of the 1D finite element solution, and you won't get this to be the case, for 2D problems and more complicated problems. The temperature boundary condition is satisfied exactly. So what I did was, I picked values for the temperature and the flux boundary condition, the length of the bar, the thermal conductivity, etc. And I assigned, I just picked that the left boundary is at 0 degrees, and you see that that matches exactly. And because what I did was I just assigned that boundary condition to that value. That's what you do with essential boundary conditions, and you can see that that's satisfied exactly. In contrast, the flux boundary condition is satisfied approximately. To see that, the flux, we look at the slope, because the flux is proportional to the slope of the temperature curve. And in the exact solution, the slope is something like that. And in the finite element solution, the slope is like that. And so you see there's a mismatch between the two. So the flux that we specify is not satisfied exactly. And that's usually the case. Whatever you have as a gradient boundary condition like the flux, that's going to be satisfied approximately, i.e. the natural boundary condition is satisfied approximately. The essential boundary condition is satisfied exactly. And when we go to structural mechanics problems, the essential boundary condition is the displacement boundary conditions. So if you're fixing, a particular edge, that's going to be satisfied exactly. But if you're putting a force, that's a natural boundary condition, and that's going to be satisfied only approximately. An important thing to consider is how to reduce the error in the finite element solution. To be able to understand that, let's go back to a slide that I showed earlier. And I talked about how one can go from a boundary value problem to a system of algebraic equations and nodal temperatures using the piecewise polynomial approximation for the temperature. So this is our assumed shape. In our case, we assumed it as, as a combination of linear polynomials. And in the process of going from the differential equation to the algebraic equations, we introduce an error called the discretization error. And we can reduce the discretization error by improving our piecewise polynomial approximation. So how do we improve the polynomial approximation? There are two ways to do this. First is to increase the number of elements, and this I think is intuitive. In our original mesh, we had 3 elements, and then we can generate a refined mesh where we have 6 elements. In our original mesh, we had, so we assume the shape is a combination of 3 linear polynomials. Now we are assuming that it's a combination of 6 linear polynomials, and that's better. The other way to improve the polynomial approximation is perhaps less apparent, which is to increase the order of the polynomial within each element. And you do that by using more nodes per element. Here I've shown a mesh with 2 second-order elements. Okay, so this would be the first element, and that would be the second element. And each element has 3 nodes. Okay, 1, 2, 3, as opposed to here where each element has only 2 nodes. And when I have 3 nodes, I can write a quadratic approximation or a quadratic interpolation between these 3 values, as opposed to here where I can only write a linear approximation, connecting 2 values. And we'll see the effect of going to the second order polynomial. So here are the results I got with refining the mesh and also increasing the increasing the order of the polynomial. This was our original solution with 3 elements, linear elements. This is the solution with 6 linear elements, okay? And you can see that it's better than with 3 linear elements. So now I have 1, 2, 3, 4, 5, 6 linear polynomial segments. And particularly you can see that the derivative here, or the slope, matches better than over here. And we know that derivative is very important because it's related to the flux. And then I'm also showing you the result with a second order polynomial with just 1 element. Okay, so this is 1 element with 3 nodes. And I have quadratic, shape in between in that element. And this is a special case where the assumed shape matches the actual shape exactly. And if that's the case, the finite element will, boom, it'll match it, it'll give you the right values. And here, with 1 element, there's no difference between the exact solution and the finite element solution when you go to the second order interpolation. In general, the second order interpolation is very effective, and here it's probably not as dramatic as over here, but it's very effective. And when we go into answers, we will see that in almost all cases the solver puts in the mid-side nodes and uses a second order polynomial rather than a first order polynomial. So then, if that's the case, what we need to do to get a better polynomial approximation is to use more elements. But we'll go and check, the order of the polynomial in one of the first cases. In fact, you will have an exercise where you're looking at doing the solution and answers using linear polynomials versus quadratic polynomials. Let's take a look at how the derivative of the temperature compares between the finite element solution and the exact solution. And the derivative of the temperature is important because it's related to the heat flux. This plot shows the comparison. On the vertical axis, I have the derivative of the temperature. On the horizontal axis, I have the distance along the bar. and the solid line is a finite element solution. The dashed line, as before, is the exact solution. So the exact solution is linear and decreasing, whereas the finite element solution is piecewise constant. And if I put up the graphic of the node sketched in, onto the to a figure of the bar, I see that over each element the derivative is constant, and that's because we assume that there's a linear variation of the temperature over each element. And it turns out that the error in the derivative is greater than the error in the temperature itself. To see that, if I say I want to look at the error at a location like that, the finite element solution says that the dt dx is that value here, okay, the corresponding value here, whereas the exact solution says it's that value, and that difference is an error. And then at the nodes, the derivative is discontinuous, which is a problem, but we can live with that problem. And from this, we can deduce that energy is not conserved for each element, and that's an important point. And to see that, let's take a look at a couple of elements. So let's say this is element 1, this is element 2, and if I draw a two-dimensional view of element 2, okay, and so I'm not showing the dimension perpendicular to the screen, and here the temperature, the way I picked the boundary conditions, the temperatures are increasing this way, so the heat is flowing this way from hot to cold. So the heat is coming in here, and I'll say that's the Q2 in, that's the heat flux coming into element 2, and if I multiply that by the area, I'll get the heat flow through there, and correspondingly this would be the heat flow going out, and if I multiply that by the area, I will get the heat flow going out. So that's the heat flux, and multiplied by the area is the heat flow. And then I also have the heat being generated in that element. That's Q times the volume, area times delta X. If energy were conserved, the heat flow going in plus the heat generated would be equal to the heat going out. But this is saying that the heat flow going in, or the heat flux going in, is equal to the heat flow going out, which means that this is equal to this, and it's not accounting for the heat being generated in the element. So what happens to this heat being generated in the element? It turns out it goes into the adjacent element. So if I draw a corresponding graphic of element 1, okay, pardon my chicken scratch, and I say the heat going in is Q1 in times the area. Now there's a jump there, which means that this is greater than that, which is non-physical, right? Because these are adjacent, so this has to be equal to that according to physical reasoning, but it's not so in a finite element solution. And you can show that that difference is exactly equal to the heat being generated in the element. So it's taking the heat being generated in the element and adding it to the heat going in through the face of the adjoining element. That's non-physical, which means that energy is not conserved for each element. It's also not conserved for each infinite similar element, because if that were the case, the differential equation would be satisfied exactly, and we saw that our finite element shape satisfies the differential equation poorly. But it turns out that the heat is, or energy is conserved in aggregate. We'll take a look at that next.